Last time there was a question, if you have a properly convex domain and you look at the set of projective transformations that fix a point in the interior, then I said that group is conjugate into the orthogonal group, and somebody asked me why. I said it is obvious. So in mathematics, a question is obvious if it can be answered within 24 hours. So I'll now explain why it's obvious. You have a Hilbert metric on the domain. If you take the unit ball, so that gives you a norm on the tangent space. So the unit ball of that norm is some compact convex set in a real vector space. Now, there's a unique ellipsoid with the same moments of inertia as that convex set. So isometries of the Hilbert metric that preserve the unit ball are a subgroup of isometries that preserve that ellipsoid. And the ellipsoid is given by a positive definite quadratic form. And so that's why it's conjugate into the orthogonal group. It's nothing to do with being strictly convex. It's the general argument. Okay, so last time I talked about a doubly elementary group. So a group is doubly elementary. It's a group of projected transformations that preserves a domain. And it's doubly elementary means that it preserves some point in the boundary of the domain and also a hyperplane that intersects the domain, a supporting hyperplane that contains that point P. So here I've drawn such a domain, a point, and a supporting hyperplane. So if you have projective space and you remove a hyperplane, you can identify what's left with affine space. And so I'm going to choose to view this domain in the affine space where I delete this hyperplane. So this is called parabolic coordinates. So here I've deleted, so this is now affine space. This hyperplane is, well, it's a projective space at infinity. It's codimension 1. So this domain is some convex set in affine space, and it's above some convex up hypersurface. And I've chosen some point Q and a supporting hyperplane there, which becomes the origin in affine space, and this becomes a horizontal axis. So this is, given a choice of a secondary point Q and a supporting hyperplane, you get this setup called parabolic coordinates. So the group of projected transformations that preserve the domain and fix the point P and this supporting hyperplane, this is this notation, that's a doubly elementary group. And in these coordinates, this doubly elementary group is an affine group. It's the following shape. The point P is vector 0 in my basis, and the last vector in my basis corresponds to the origin. And so the projective space at infinity is a projectivization of all these vectors where I leave out the 0th vector. And in these coordinates, this doubly elementary group is a subgroup of this group. So the first column is 0 except the first entry, and the last row is 0 except the last entry, where it's a 1. This is an affine group. There is a one-parameter group of transformations, which in this picture is vertical translation upwards. And this is something called the radial flow. And if I take the boundary of omega and move it upwards by the radial flow, I get some translated hypersurface. It's called an algebraic horosphere. And these algebraic horospheres foliate omega, and they are preserved by projective transformations in this group. In these coordinates, the radial flow is given by this matrix. And Okay. So in particular, this leads, if you apply this to hyperbolic space. So in hyperbolic space, if you take one way to think of hyperbolic space, you take a round disk in hyperbolic space, and we're going to take a point in the boundary of this disk and a supporting hyperplane. If you apply parabolic coordinates to hyperbolic space, what you get what's called the parabolic model of hyperbolic end space. So the parabolic model of hyperbolic end space, it's a subset of Euclidean end space, and it's a subset in these coordinates where the x1 coordinate is bigger than the sum of the squares of the other coordinates. So that's a paraboloid. So the set of points above the paraboloid is called the parabolic model of hyperbolic space. And if you take this paraboloid and move it vertically upwards by Euclidean translation, you get a horoball. So I described that in the upper half space model the other day. So here it's the points lying above a hyperboloid, and I'm calling that a standard horoball. The group of parabolic transformations that preserve this point P is a doubly elementary group. And in these coordinates, it's this group. So it's this upper triangular group where you have x2 through xn in the first row and the last column, and then this entry in the top right corner is the sum of the squares. The boundary of this paraboloid is given by the orbit of the origin under this group. So it's read off actually by the last column here. So the last column shows you the x1 coordinate is a graph over the other coordinates. The possibilities for cusps in hyperbolic manifolds correspond to choices of lattice in this group of parabolics. And so the possibilities for lattices in here correspond to, well, so a lattice in here is given by a homomorphism, a discrete subgroup isomorphic to z to the n minus 1. So that's given by an element of SLn minus 1r. On the other hand, rotating the intrinsic geometry on a horoball is Euclidean. And if I kind of rotate the horoball, it doesn't change the geometry. So in fact, cusps in hyperbolic manifolds correspond to elements of SLn minus 1r up to the choice of an element in the orthogonal group. So that's a classification of Euclidean tori up to the similarity. It's also the classification of cusps in a hyperbolic manifold. And so the group of parabolic transformations is a group of dimension n minus 1. It's a Euclidean group r to the n minus 1. You can enlarge it to be a group of one bigger dimension by adding onto it this radial flow group, the group of vertical translations. And when you do that, you get something we call the extended translation group. So it's got a codimension 1 subgroup, which are a group of parabolics that preserve the domain. And then there's this extra one-dimensional group that is the parabolic flow. So this picture is going to get generalized when we talk about generalized cusps. So generalized cusp is, well, I'm going to talk about generalized cusps where the fundamental group is free abelian. There's a more general discussion, but I'm not going to discuss that. So the basic point is, so we're going to be thinking about a properly convex domain, omega, and a discrete group of isometries acting, a discrete group of projective transformations preserving that domain, this group gamma, and this group gamma is free abelian. And the key property that gamma has is that it's actually conjugate into the group of upper triangular matrices with positive entries on the diagonal. So this is the Borel subgroup in here, it's the identity component of the Borel subgroup, the upper triangular group with positive entries on the diagonal. So this is the key fact, a key fact that's used in the classification of generalized cusps, that these discrete groups are actually lattices in a certain kind of connected Lie group. So, I welcome questions, remember. Talk without questions is a failure. I'm going to go through the proof of this. So we've got this abelian group acting on this properly convex domain. I want to show its conjugate into upper triangular matrices with positive entries on the diagonal. So the first step is to argue that, well, it's certainly conjugate. If I complexify, if I use complex numbers, this group is certainly conjugate into the upper triangular group over the complex numbers. That's just algebra. The point is that, well, there's this weight space decomposition. So what's a weight? It's a homomorphism from the group into the complex zero complex numbers under multiplication, a homomorphism with the property that the generalized weight space is non-zero. So if you think about the Jordan normal form, you know, if you take some eigenvalue and you think about the Jordan blocks for that eigenvalue, that's the kernel of the matrix minus lambda times the identity to some large power, the large power being the dimension of the group you're working in. So a weight is a homomorphism of the group into non-zero complex numbers with the property that the generalized weight space isn't zero. And the point is that if this group is abelian, there is a weight. And that just comes, that's an easy argument by thinking about eigenvectors. So there is a weight, and then a simple induction argument tells you once you know there's a weight, you can quotient out by the generalized weight space, argue by induction, and that's the proof that gamma reserves, gamma is conjugate into some upper triangular group of over the complex numbers. So now the geometry comes in to argue that actually all these weights are actually real. All these weights take values in the positive real numbers. So this is where we're going to use some geometry, the fact that this group preserves a properly convex domain. So we'll work in the projectivization of Rn plus 1. So Rn plus 1 is some vector space. And this vector space can be decomposed as a direct sum of generalized weight spaces. So we can take the generalized weight spaces where the weights are real, and the generalized weight spaces where the weights aren't real. And we want to show that there aren't any ones of this form. So the generalized weight spaces where the weights aren't real, we can combine the weight space for a complex weight and its complex conjugate and get a decomposition of V into real vector spaces corresponding to real weights and pairs of complex conjugate weights. And I want to show that there aren't any of these, and actually V decomposes as a direct sum of real weight spaces. I want to show that this vector space B is zero. And so this is where the kind of geometry comes in. So how do we do that? Well, we pick a point, a vector that corresponds to a point in the omega, and that vector can be written as a sum of vectors in, some vector in A, and then some vectors coming out of these generalized weight spaces for the complex weights. And I'm going to choose such a point where the number of complex coordinates is as small as possible. So I want to argue that there is some choice of vector where all the BI's are zero and A is not zero. So in particular, I'm arguing that to start with, that A is not the zero vector space. There is at least one real weight. And so how do you do that? Well, you take some vector where the number of I's for which BI is non-zero is as small as possible. And we can reorder so that we can assume that B1 is not zero. And now, so the fact that this weight isn't real means there's some element in the group. So the weight of this element corresponding to this non-real weight of this element isn't a real number. It's some complex number. So now you take the convex hull. This vector lies in this vector space B1, and this vector space B1 is invariant under the action of gamma. So we can take the orbit of this vector in B1 and take its convex hull. And so that's some convex set in B1. And the claim is that the zero vector is in that convex hull. And the reason is, if the zero vector is not in the convex hull, this should actually say closed convex hull, actually. So you take the closed convex hull, the smallest closed convex set containing the orbit, and a claim zero isn't in there. And the reason is, if zero is not in that convex hull, then we can take the image in the unit sphere in positive projective space. We can take the image of this convex set in positive projective space, and you get a closed convex set. And this closed convex set is mapped to itself by gamma. And so there's some fixed point in that convex set. And that fixed point then is it was a positive eigenvector for gamma in the vector space B1. But all the vectors in B1 have complex eigenvalues for gamma, so that's the contradiction. So this convex hull, the orbit of this vector under X, has the zero vector in it. So that means there's some convex combination of the orbit of B1, some finite convex combination, which gives zero, because zero is in the convex hull. So some finite convex combination of vectors of the form gamma to the power I times a vector B1, which gives a zero vector. So now, I'm going to lift to the double cover of projective space. So we've got this convex domain omega in projective space. We can lift to the double cover, the positive projective space of V. And corresponding to that double cover, there's a cone, the set of positive multiples of vectors in omega. So we've got this now. Omega lives in the unit sphere. The cone is some cone in the vector space V. And the original vector I had, remember that the original vector X had some non-zero B1 coordinate in it. If I take the corresponding convex combination of not of the orbit of B, but the orbit of X, I get a new vector X prime, the corresponding combination of the orbit of X. And because this is a convex set, this convex combination is in the convex set. So get a new vector, a new point whose projectivization is in omega. And this new point has got zero B1 coordinate. So it contradicts the minimality of the number of non-zero complex coordinates in X. And so that that means that I can choose a vector X in the vector space A, a non-zero vector in the vector space A corresponding to a point in omega. In particular, this set of real weights is not empty. There are some real weights. And so if I take the projective subspace corresponding to this vector space, that's some projective subspace, it intersects the domain omega in some properly convex subspace that's preserved by the group gamma. So inside this domain omega, I've now got a domain, a convex domain of smaller dimension, W, that's preserved by gamma. And now there's a little algebraic topology argument. So the point is that the quotient of the original domain by gamma is homotopy equivalent to a closed manifold. It's homotopy equivalent to a torus of dimension n-1. And so the quotient of W by gamma is also homotopy equivalent to the same manifold. So that means that the dimension of this domain W has to be the same as the dimension of the domain omega. They have the same dimension because of, because this group gamma is a K-pi1 and omega is contractible. And so, so this means that, in fact, A is the entire vector space V, and there are no complex weights at all. So this means that all the weights are real. And actually, the same argument rules out negative weights as well. The point was that you actually have a positive eigenvalue. So this argument tells you all the weights that are actually positive reals. So that's the proof. And the consequence of that is following. So if you start out with this properly convex manifold, whose fundamental group, so we're dealing with something of n dimension n, and the fundamental group is z to the n-1, then this group gamma is a lattice in a connected abelian Lie group T. What is T? Well, since all these matrices are in the upper triangular group, I mean, the exponential map from the Lie algebra is an isomorphism, is surjective onto the positive upper triangular group. Every element in gamma has got a well-defined logarithm, and matrix is positive, it's got a well-defined logarithm. And then if you take the sub-algebra of the Lie algebra defined by these matrices and exponentiate it out, you get a Lie group of dimension n, you get a Lie group, an abelian Lie group of dimension n-1 that contains gamma. And this is a connected Lie subgroup in the positive upper triangular group. So the conclusion is that this discrete group gamma is actually a lattice in a connected Lie group T. And now, if you take a point in the boundary of the original domain and you orbit it by this connected Lie group, then you get a convex hypersurface. And the group gamma preserves this convex hypersurface. And so you get a possibly new domain where this new domain is preserved by this Lie group. And so the conclusion is that a maximal generalized cusp is equivalent to a homogeneous one. A homogeneous generalized cusp is a cusp for which there is a transitive action of projective transformations on the domain, a transitive on the boundary of the domain. So it reduces the problem of figuring out what the possibilities for generalized cusps are to thinking about domains where you have a transitive group acting on the boundary of the domain. So Ariel Leitner, in her thesis, discovered what the possibilities for generalized cusps in three manifolds are. She found there are four types. And this type here, you should recognize as a standard this corresponds to cusp in a hyperbolic manifold. This is a standard group of parabolics in the parabolic model of hyperbolic 3 space. That's type 0. Type 3 is a subgroup of the diagonal group. It's an affine group, and it depends on three parameters, psi1, psi2, and psi3. These are positive numbers. And then there are these two other families. So in dimension 3, there are four kinds. She discovered four kinds of translation group. And so in dimension 3, a generalized cusp is given by a lattice in one of these four types of Lie group. So this leads to the classification of generalized cusps. So it's a kind of generalization of what I just said. So we're going to think about generalized cusps in dimension n. So here is a family or finite collection of Lie groups. You fix a dimension n, and given the dimension n, you pick a type t. T is an integer between 0 and n. And depending on what t is, there's a Lie group and an affine group which is isomorphic to r to the n. And what you've got here in the top left corner, there's a diagonal group. And in the bottom right corner, this block here is the extended translation group for the standard cusp in hyperbolic geometry. So this is an identity matrix. So we've got some entries along the top row, and in the last column, everywhere else is zeros. So in the special case of type 0, this thing in the top right corner isn't here. You've just got this. And this block here is what I call the extended translation group for hyperbolic geometry. So the group of parabolics is where this entry in the top right corner depends on these entries along the first row. When you throw in this extra one parameter group, you get this bigger group of one dimension bigger, where this can be anything. At the other extreme, this block might not be here, and then you've got a diagonal subgroup where it's an arbitrary diagonal subgroup. Well, the entries on the diagonal are positive because it's the exponential of something, and there's a 1 in the bottom right corner. So these are things called extended translation groups. And now we're going to pick out a subgroup of codimension 1 in here. This subgroup of codimension 1 is picked out by taking a homomorphism from this Lie group to R and taking the kernel of that homomorphism. And what the homomorphism is given by this formula here. By the way, I've taken the exponential of the diagonal matrix. I'm kind of thinking really in the Lie algebra here. These are Lie algebra coordinates. And so you can think of this as a homomorphism from the Lie algebra into the reals. And it's given by, well, you take some linear combination of the diagonal entries here, and the coefficients are non-negative. Sorry, the coefficients are actually strictly positive, and then this entry. So you take this homomorphism and you take its kernel. And so that's a subgroup of this group of codimension 1. And that's a Lie group of codimension 1. And so there's lots of choices of Lie group of codimension 1 corresponding to a choice of this homomorphism. So what is a generalized cusp? Answer, you choose one of these homomorphisms, you take the kernel, you've got this Lie group now, depending on this choice of homomorphism, you take a lattice in this Lie group, and that lattice, gamma, is a group of projected transformations that preserves a properly convex domain that gives you a generalized cusp. So this is a kind of interesting construction because there are finitely many choices of type. In dimension 3, there were 4 types. But then you get to choose a set of n numbers, which are, and that should say bigger than or equal to 0. So you then get to choose some non-negative real numbers, and you can put them in order, decreasing order. And this is something called the Weil chamber. So you pick a type. Corresponding to the type, you then get to, well, I should say it the other way around. You pick a point in the Weyl chamber. The number of non-zero coordinates tells you what the type is and therefore defines a Lie group. So the conclusion is that for every point in the Weyl chamber, there is a Lie group isomorphic to R to the n minus 1, and a lattice in that Lie group gives you a generalized cusp. So these Lie groups are called translation groups. There's infinitely many of them, depending on the choice of a point in the Weyl chamber. They're codimension 1 subgroups of one of finitely many Lie groups, depending on the type. And the basic result is that every translation group is conjugate in the affine group to one of these Lie groups. So it follows that every generalized cusp is a lattice in one of these groups. Yeah. Right. Yeah. Okay. Right. So the question is, why do these Lie groups preserve a properly convex domain? You can just check they do. That's it. The fact they preserve. That's why these coordinates, by the way, have to satisfy these conditions. So, for example, if you look at the diagonal groups, so you know, if these aren't positive, the orbit of a point under this 2-parameter group won't be a convex hypersurface, it will be some non-convex hypersurface. So the positivity condition is what's required in order for the orbit of a point to be a convex hypersurface. This doesn't preserve a proper convex domain, no. These subgroups do. That doesn't. The orbit of a point under this group is a convex hypersurface in affine space. The orbit of a point under this group is the product of a simplex and an affine space. It's not a properly convex. It's one dimension. It's an open set in. It's an open set in affine space. It's this codimension 1 subgroup where the orbit's a convex hypersurface. Okay, so the classification result is this tells you what the possibilities of generalized cusps are. And what do they look like? So if you take one of these groups, you orbit a point, you get some convex hypersurface in affine space. You take the set of points above that, that's the domain omega. Now, there's a projection, there's a linear projection of affine space onto a simplex where you take the coordinates corresponding to the x coordinates. That projects this domain onto a simplex. And the preimage of a point in this simplex, well, it's a subspace here, which is a copy of the standard horoball. So the standard horoball is the, it's this thing in, it's a horoball in the hyperbolic space. So the domain you get for these, domains you get for these groups, there is some kind of combination of the simplex and standard horoballs. Okay, so at this point, there are a finite number of families of generalized cusps, depending on the type. And they look very different. And so the surprise is actually that these different types all fit into a continuous family. They continuously transition from one type to another type. And so, in other words, so this is the classification of generalized cusps. I've told you what they are. I now want to describe the moduli space. And it would be very nice. So if you think about hyperbolic structures on a surface, they're parameterized by points in Tillmann space. And you can find a continuous map that takes a point in Tillmann space and gives you a corresponding discrete group. Gives you a hyperbolic surface. In other words, okay. So what you might hope is that there is a continuous map that takes a point in moduli space and continuously gives you a discrete group corresponding to the generalized cusp. And that probably doesn't exist. But something close to it does exist. So the classification of generalized cusp, what do? We take a point in the Weyl chamber. That determines a Lie group, and you take a lattice in that Lie group. What we're going to do is take something called the blown up Weyl chamber. So this is a blow up in the sense of algebraic geometry. So the Weyl chamber, set of points in Euclidean space, all the coordinates are non-negative, and I've ordered them so they're increasing. The blown up Weyl chamber, what is that? Well, it's a point in the Weyl chamber together with a set of points, kappa, that lie between 0 and 1. And the kappas aren't arbitrary. We satisfy these equations that kappa I times lambda I is lambda 0. So if lambda 0 isn't 0, kappa I is determined. It's lambda 0 divided by lambda I. But if lambda 0 is 0, then these kappa i's are arbitrary, anything between 0 and 1. So this is called the blown up Weyl chamber. So the deal is the following. For every point in the blown up Weyl chamber, I'm going to define a Lie group depending on the point in the blown up Weyl chamber. This is a Lie group of dimension n minus 1. So these Lie groups are going to vary continuously in lambda and kappa. And if I take a lattice in one of these Lie groups, that gives me a generalized cusp. So this finite, so here we had, depending on the type, each type, there was a continuous family of codimension 1 subgroups in that type. So a finite set of continuous Lie groups, continuously varying Lie groups. Here, there's just there are more parameters, but there's a continuously varying family of Lie groups here corresponding to these parameters. And the deal is that each one of these Lie groups is conjugate to one of the Lie groups in the previous discussion. In fact, this Lie group corresponding to parameters lambda and kappa, it's conjugate to one of these other translation groups. Which one doesn't depend on kappa, it only depends on lambda. And the deal is that the relationship between lambda and psi is given by this. So, yeah. Where does phi come from? Yeah, okay. So this comes from the classification, right? So I'm giving the logic is I'm pulling out of a hat some groups, and then I'm going to prove later on these are the only possible groups. So where this comes from is one answer is you stare at these and you think what's going on, and you guess that this is what is going on, and then you prove that this is what is going on. Okay, that. Sorry, say it again. You get a kernel on that side. Yeah. No, there's no constraint on the wires. You're right. So what this so if you think what this means is so here, for example, in this group, so you pick a psi1 and you get this group is what's going on here. So the homomorphism here was Z minus psi1 x1. It gave you that Lie group. So okay, so there is finite numbers of types of translation groups. I want to give you an abstract argument that something like this has to happen. So something like this has to happen. And the argument is the following. So all these Lie groups have to form some kind of connected family. And the reason is that if you, so you might pick a particular type. So what does a type mean? It means you've got some number of coordinate psi i's that are positive and the other ones are zero. And you get to pick a psi and then you can pick a lattice in that Lie group. So let's forget about the lattice. Let's just think about the Lie group. So if I pick some point in the Weyl chamber, that gives me this gives me this codimension 1 subgroup, and the orbit of a point under this codimension 1 subgroup is a convex hypersurface in affine space. As they vary the size, this convex hypersurface changes. In particular, if I let one of the sides go to zero, this convex surface is flattening out in some directions. In the limit, it's not going to be strictly convex anymore. But I get to conjugate the group. I've got this hypersurface that's flattening out in some direction. I can do an affine map that stretches that direction so it's not flattening out anymore. So as some coordinate size going to zero, the surface is flattened out. I can do an affine map. I can conjugate to prevent the surface flattening out. So there has to be some limiting surface with some limiting translation group on it that corresponds to what's going on when one of these psi's goes to zero. So something like this has to happen. One other comment is that when lambda 0 is not 0, all these coordinates are not 0, then one is talking about a subgroup of a diagonal. The translation group is a subgroup of the diagonal group, the positive diagonal group. It's a codimension 1 subgroup, a special subgroup because the orbit of a point's convex. The other groups where the lambda 0 is 0, you're free to choose kappa to be 0. And when you choose kappa to be 0, this term isn't here. And if you think of, okay, well, right, so this term isn't here. And if the weights are distinct, if that term's not there, this group is conjugate to a diagonal group. So somehow putting all that together, well, there's a longer explanation in the paper about where this comes from, but you kind of, this discussion about something like this has to exist and you play around and this comes up. Anyway. Okay, so a generalized cusp is given by a discrete group acting in a certain way in a properly convex domain. That discrete group is a lattice in a Lie group. You take a point in affine space, you orbit it by that Lie group, you get a convex hypersurface. So another way to think about actually what generalized cusps are is, what the possibilities are, Generalized cusps correspond to lattices in certain family of Lie groups. What are the Lie groups? Answer. Think about affine space. Think about having a strictly convex hypersurface in affine space, which admits a simply transitive group of affine transformations, preserving it. Those are what the possibilities are. So one is classifying, if you like, strictly convex surfaces in affine space that are properly embedded. Well, an example of a strictly convex surface is a sphere. So we want a non-compact, strictly convex surface in affine space, which admits a transitive group of affine maps acting on it. Those groups are these groups, and lattices in those groups are generalized cusp groups. So, there's a metric. If you have a strictly convex surface in affine space, there's a metric on that surface coming from the second fundamental form. And so we've got a smooth, strictly convex hypersurface S in affine space. And suppose, well, you've got two of them. And suppose you've got an affine map that sends one strictly convex hypersurface to the other, or for that matter, sends a strictly convex hypersurface to itself. Well, there's a metric on that strictly convex hypersurface coming from the second fundamental form. And the fact is that that affine map is a conformal map. So, for example, if you take the sphere, there's an affine map that rotates the sphere. And of course, that is an isometry. It's a conformal map. But more generally, if you have one of these non-compact hypersurfaces, the same result is true. That we're looking at surfaces, these strictly convex hypersurfaces in affine space, which have a transitive group of isometries acting on them. So as a consequence of this fact, if I take the metric on this surface that's given by the second fundamental form, this affine group is acting conformally on the surface. And so it follows actually that the metric on the surface coming from the second fundamental form, the surface with this metric on it is actually conformally equivalent to Euclidean space and therefore actually isometric to Euclidean space. So anyway, so this basic fact, if you have a smooth strictly convex hypersurface in Euclidean space, an affine map, it preserves, it induces a conformal map. Why is that? So here's an intuitive explanation. So you've got this convex hypersurface and you've got this metric coming from the second fundamental form. How do you understand that? So you could take a point on the hypersurface, you take the tangent hyperplane, move the tangent hyperplane off itself slightly. It will now intersect the hypersurface in some infinitesimal ellipsoid. Now, affine maps send parallel hyperplanes to parallel hyperplanes. It sends ellipsoids to ellipsoids. And that infinitesimal ellipsoid determines the quadratic form. And so that's why this action is conformal. So as a consequence, a generalized cusp, it's got a boundary coming from this convex hypersurface in affine space, and that boundary has got a metric on it coming from the second fundamental form, and that metric is actually a Euclidean metric. So there's this kind of intrinsic Euclidean geometry on the boundary of a generalized cusp. So this leads to a kind of geometric classification of generalized cusps. So I mentioned yesterday, if you have a cusp in a hyperbolic manifold, the boundary of the cusp is a torus, and it's got a Euclidean structure defined up to scaling. It's got a similarity structure. So something similar happens for a generalized cusp, but there's more data. And I'll describe that next time.